In the silent, high-stakes arena of fifth-generation air combat, the battle is won before the engines ever ignite. It is a war of physics, not pilots, a contest of radar-scattering geometries, heat-suppressing materials, and sensor fusion algorithms that decide victory from 100 miles away. Every design choice is a gambit, every innovation a potential checkmate. Into this unforgiving environment, the Shenyang J-31 was born, not from a state mandate, but as a corporate longshot. It endured a turbulent adolescence of shifting identities, public mockery for its smoky engines, and a profound transformation into the formidable, carrier-borne J-35. This machine is more than a new piece of hardware. It is the physical manifestation of a nation's strategic will, an industrial marathon, and a geopolitical play that could fundamentally alter the balance of air power for decades to come. The genesis of the Gear-Falcon was, by the standards of major Chinese military programs, unorthodox. It did not emerge from a clearly defined state requirement, but was presented as a private venture by the Shenyang Aircraft Corporation, SAC, a key subsidiary of the state-owned Aviation Industry Corporation of China, AVIX. This corporate-led initiative was a curious departure from the typical top-down, state-directed model, with AVIC's chairman Lin Zuoming publicly asserting that the aircraft's development was funded entirely by the company, with no initial investment from the military. This claim, while plausible on the surface, likely masked a more nuanced strategic reality. In a system where major industrial efforts are intrinsically linked to national strategy, the private venture was almost certainly a state-sanctioned but corporately fronted project. This approach provided a valuable strategic hedge, allowing China to explore a medium-weight, twin-engine stealth fighter concept in parallel to the larger state-backed Chengdu J-20 program, mirroring the high-low mix philosophy of the American F-22 and F-35. It created a low-risk test bed for new technologies and design concepts, insulating the official military budget from the high probability of early-stage failure while positioning the state to capitalize on any success. The aircraft's early life was marked by a confusing flurry of designations, a sort of programmatic identity crisis that reflected its unofficial status. While SAC's official nickname was Gear-Falcon, Guying, it was variously referred to in media reports as the F-60, the J-21, or even the Snowy Owl, Yuexiao, a menagerie of names for a machine yet to prove its mettle. The first tangible proof of its existence came on October 31, 2012, when prototype number 31,001 conducted its maiden flight. It was a tentative 10-minute affair, with the aircraft's landing gear remaining down for the duration as it was cautiously escorted by two J-11 fighters. Despite its brevity, the flight was a milestone, making China only the second nation after the United States to have two distinct stealth fighter designs in active flight testing at the same time. However, the program's subsequent public appearances were far less auspicious. Its flying display at the 2014 Zhuhai Air Show became infamous. The prototype was visibly underpowered, struggling through maneuvers, and most damningly, trailing thick plumes of black smoke from its twin engines. This unsolicited, high-contrast visual tracking signature was a clear indictment of its power plants. Two Russian-made Klimov RD-93 afterburning turbofans, the same engines used to power the much smaller and lighter PAC JF-17 Thunder. Western observers were unsparing in their critique, noting that the aircraft bleeds a lot of energy and that the pilots seemed to have a difficult time keeping the nose up, even in a clean configuration. Paradoxically, this very public humiliation may have been the program's salvation. The spectacle of a next-generation airframe hobbled by antiquated, foreign-sourced engines created an undeniable and politically potent justification for a massive state-level investment to solve the core problem. It laid bare the strategic vulnerability of relying on external suppliers for critical military components, and likely served as the catalyst that forced military planners to either abandon the Gerfalcon or commit fully to its maturation, particularly the development of a suitable domestic engine. The program's trajectory shifted decisively when the People's Liberation Army Navy, PLAN, began to show serious interest. Naval planners tasked with equipping a new generation of aircraft carriers saw in the FC-31's twin-engine, medium-sized airframe the potential for a carrier-capable stealth fighter, a critical component for their blue water ambitions. This naval requirement provided the project with a clear purpose, a powerful patron, and the state funding it had previously lacked. The evolution was rapid and profound. The second flying prototype, Maina No. G. 31003, which took to the air on December 23, 2016, was already a significant redesign of the original airframe. Its length was increased from 16.8 meters to a more substantial 17.3 meters, and its maximum takeoff weight, MTOW, was raised from 25,000 kilgas to 28,000 kilgas, a clear nod to the structural strengthening required for the brutal physics of carrier operations. This process culminated in the aircraft that would become unofficially known as the J-35. Its first prototype made its maiden flight on October 29, 2021, bearing the unmistakable hallmarks of a naval fighter. The airframe was equipped with a robust twin-wheel nose gear assembly featuring a catapult launch bar, a wing-fold mechanism to conserve precious deck space, and other structural reinforcements necessary to withstand the controlled crash of an arrested landing. The J-35 is not merely a new aircraft, it is the linchpin of an entirely new naval aviation doctrine for China. Its development is inextricably tied to the Type 003 Fujian aircraft carrier, a vessel equipped with advanced electromagnetic catapults similar to the American EMALs. Without a catabar-capable stealth fighter, the Fujian would be a capital ship without its primary sword, unable to launch heavily armed, fully fueled aircraft that can penetrate modern air defenses. The J-35 is the weapon that unlocks the carrier's true potential, transforming the entire carrier strike group from a regional defense platform into a credible instrument of long-range power projection. The successful completion of catapult launches and arrested landings by the J-35 from the Fujian, publicly announced in September 2025, was therefore a milestone of immense strategic significance, signaling the birth of a new era in Chinese naval power. In parallel, a land-based variant, designated the J-35A, has also been developed for the People's Liberation Army Air Force, PLAAF. This version is distinguished by a lighter, single-wheel nose gear and different wing and vertical stabilizer designs, indicating a thoughtful strategy to maximize commonality between the two services while tailoring each airframe to its specific operational environment. This evolution, driven by the harsh requirements of naval aviation, is a clear example of convergent design. While the J-35's overall shape bears a strong resemblance to the American F-35, the specific modifications for navalization, the beefed-up landing gear, the folding wings, the launch bar, are dictated by universal, non-negotiable laws of physics. Carrier operations demand these features, forcing any nation's engineers, whether in Fort Worth or Shenyang, to arrive at remarkably similar solutions. The entire development arc of the J-31, J-35 program can be viewed as a saga of propulsion, with the airframe's capabilities consistently paced and constrained by the engines available to power it. This journey unfolded in three distinct phases, mirroring the maturation of China's indigenous aero-engine industry. The first phase was defined by a reliance on a Russian crutch. The initial prototype was powered by two Klimov RD-93 turbofans, each generating a modest 84 to 85 kilonewtons of afterburning thrust. These engines were a stopgap, a way to get the airframe flying, but they were woefully inadequate, for a fifth-generation fighter, leading directly to the underperformance and infamous smoke trails of its early displays. This dependency also created a strategic liability. For a program ostensibly aimed at export, the use of Russian engines meant that Moscow could effectively veto sales to potential customers such as Pakistan if it came under diplomatic pressure from rivals like India. The second phase marked the transition to a domestic stopgap, the Guizhou WS-13 Taishan engine. The WS-13 was essentially a Chinese-developed and improved derivative of the RD-93, cleverly designed to fit the same physical footprint, which simplified its integration into the existing airframe. More advanced variants, like the WS-13E, pushed the thrust up to a more respectable 92 to 93 kilonewtons, and crucially, they were smokeless. This solved the aircraft's most embarrassing public relations problem, but still fell short of providing the thrust-to-weight ratio needed for the kinematic performance expected of a true peer competitor. The third and current phase centers on the intended powerhouse, the Guizhou WS-19, codenamed Huangshan. This is not an iterative improvement, but a completely new engine design, reportedly leveraging advanced technologies developed for the J-20's high-performance WS-15 engine. The WS-19 represents a quantum leap in capability, with a maximum afterburning thrust in the range of 98 to 116 kilonewtons, approximately 22,000 to 26,000 pounds force, and a target thrust-to-weight ratio of around 10.1. This engine is the key that will finally unlock the J-35's full performance potential, enabling a top speed of Mach 1.8 or higher and potentially the coveted ability to supercruise, fly at supersonic speeds without the fuel-guzzling use of afterburners. This progression reveals that the engine has been the program's critical path dependency. The airframe has, in essence, been waiting for the propulsion technology to catch up. The operational viability of the entire J-35 fleet is therefore wholly contingent on the successful mass production and long-term reliability of the WS-19. This multi-tiered engine development also provides a sophisticated mechanism for export control. China can market the FC-31 export variant equipped with the capable but less advanced WS-13E engine, offering a fifth-generation light fighter to international customers. Simultaneously, it can reserve the cutting-edge WS-19 for its own domestic J-35 fleet, thereby ensuring the Plan and PLA-F maintain a distinct and permanent technological overmatch against the very clients they supply. This creates a deliberate capability gap, a hallmark of mature arms exporters, and points to a highly calculated long-term strategy for the program. The anatomy of the J-35's invisibility is a study in the modern principles of low observable design, blending aerodynamic shaping, advanced materials, and careful systems integration. The airframe itself adheres to the classic stealth shaping philosophy, featuring a chined fuselage, trapezoidal planform wings, and canted vertical stabilizers, with the edges of control surfaces carefully aligned to deflect incoming radar waves away from the source emitter rather than reflecting them back. Two of the most critical elements of this shaping are the engine inlets and nozzles. The aircraft employs diverterless supersonic inlets, DSI, which use precisely sculpted bumps on the fuselage to manage airflow at high speeds without the need for complex, heavy, and radar-reflective moving ramps found on older designs. Behind these inlets, the engine faces are concealed by serpentine S-ducts, which curve to block any direct line of sight to the highly reflective turbine blades, a primary source of radar return from the frontal aspect. At the rear, later prototypes and production models feature engine nozzles with serrated or sawtooth edges, a design that helps to scatter radar waves and break up the aircraft's thermal signature, making it harder to detect by infrared sensors. The aircraft's skin and underlying structure represent an area of significant technological advancement. Early speculation suggested the FC-31 relied on simpler applied stealth coatings rather than the more advanced baked-in fiber mat composites used in American designs. However, more recent pronouncements from Chinese state media regarding the J-35 make far more sophisticated claims. Official reports credit its low observability to domestically developed metamaterial technology, a class of engineered materials with properties not found in nature, designed to manipulate electromagnetic waves. One particularly intriguing report details a novel radar-absorbing material inspired by ancient Chinese double-sided jacquard silk weaving techniques. This technology allegedly integrates conductive yarns into a durable textile matrix, creating a structure that can effectively absorb radar waves across a wide frequency spectrum, specifically 8 to 26 GHz. This focus on advanced materials is central to the public relations battle over the aircraft's radar cross-section, RCS. Chinese state media has metaphorically touted the J-35's RCS as being smaller than a human palm. This is a deliberately chosen phrase, as Western analysts have translated it into a numerical estimate of approximately 0.01 square meters, or a range of 10 to 100 square centimeters. This figure is clearly intended to be benchmarked against the American F-35, whose frontal RCS is often compared to the size of a golf ball, or roughly 15 square centimeters. This metaphorical jousting is a form of information warfare, a calculated effort to shape global perception and position the J-35 as a direct peer to the F-35 in the critical metric of stealth, a claim that is strategically potent even if it remains operationally unverified. Furthermore, the Chinese reports on their novel coatings emphasize not just radar absorption, but also operational durability, claiming the material can withstand 93.5 megapascals of tensile stress, and explicitly contrasting this with the well-documented maintenance challenges and high costs associated with the delicate stealth coatings on the F-22 and F-35. This suggests a conscious design effort to engineer a more robust and field-maintainable stealth solution, targeting a known operational weakness of its primary competitor. A higher sortie rate due to lower maintenance demands could prove to be a significant asymmetric advantage in a protracted conflict. Beyond the physical airframe lies the aircraft's nervous system, the suite of advanced sensors, and the software that binds them into a coherent whole. Here, the J-35 is equipped with hardware that mirrors the triad of sensors defining its American counterpart. The primary sensor is an active electronically scanned array, AISA, radar, likely the KLJ-27A for export models, and a more advanced indigenous system for domestic J-35s, providing long-range detection and tracking capabilities. This is complemented by a chin-mounted electro-optical targeting system, EOTS, a faceted window-housing powerful infrared cameras for passive detection, tracking, and targeting of both air and ground threats, much like the F-35's EOTS. Finally, the aircraft is reported to feature a distributed aperture system, DAS, a network of 6 infrared sensors embedded around the airframe to provide the pilot with a 360-degree spherical view of the surrounding battle space, enabling unprecedented situational awareness and missile threat detection. The pilot interacts with this torrent of data through a modern glass cockpit, dominated by a large single-piece multifunction touchscreen display and a helmet-mounted display system, HMDS, that projects critical flight and targeting information directly onto the pilot's visor. However, the presence of this hardware is only half the story. The truly revolutionary and most challenging aspect of a fifth-generation fighter is sensor fusion. This is the ability of the aircraft's onboard computers to seamlessly ingest data from its own radar, EOTS, and DAS, as well as from off-board sources via data link, and fuse it all into a single, intuitive, and actionable picture of the battlespace. While China has proven its ability to manufacture the physical sensors, the maturity of its sensor fusion software remains the program's greatest unknown and the most significant potential capability gap when compared to the F-35. The F-35 software is the product of over a decade of iterative development, multinational collaboration, and the analysis of vast amounts of real-world operational data, a developmental ecosystem the J-35 program has not had. This is the fundamental challenge. The hardware is a solvable engineering problem, but the software that grants true informational dominance is a war of algorithms, a battle that is won through millions of lines of code and years of refinement. Yet China may not need to perfectly replicate the F-35's globally networked model. For its primary strategic goal of regional anti-access area denial, A2AD, a good enough sensor fusion capability could be sufficient, provided it is tightly integrated with China's vast terrestrial and space-based network of radars, satellites, and naval sensors. The J-35's design philosophy may not be to create a self-reliant, globally interoperable data node like the F-35, but rather a highly effective regional predator optimized to fight and win within its own integrated battlespace network. The lethality of any fighter is ultimately measured by its talons, the weapons it carries into combat. In this regard, the J-35 appears to have been designed with a clear emphasis on air-to-air combat and magazine depth. Its central internal weapons bay is reportedly capable of carrying between 4 and 6 beyond visual range air-to-air missiles, BV rams. If a 6-missile internal loadout is standard, it would confer a significant 50% advantage in stealthy engagement capacity over the F-35's typical internal load of 4 AIM-120 AMRAAMs. This suggests a design philosophy optimized for achieving a decisive first salvo in an air superiority role. The doctrine appears centered on detecting an adversary at extreme range, likely cued by off-board assets like the KJ-600 Airborne Early Warning and Control (AEW&C) aircraft, and launching an overwhelming volley of long-range missiles to attrite enemy forces before a visual range engagement can occur. The primary weapon for this role is the formidable PL-15 missile, a weapon featuring a dual-pulse rocket motor for high terminal energy, an advanced ASA seeker for improved tracking and countermeasure performance, and a blistering top speed exceeding Mach 5. Its effective range is reported to be in excess of 200 kilometers and perhaps as much as 300 kilometers, outranging many of its Western counterparts. For close-in combat, the aircraft carries the PL-10, a highly agile imaging infrared-guided missile with high off-boresight capability, allowing the pilot to engage targets far to the side of the aircraft's nose. Further developments hint at an even greater focus on internal carriage, with speculation surrounding a new compressed carriage missile, possibly designated the PL-16, designed with folding fins to maximize the number of weapons that can be packed into a stealth fighter's bay. A conceptual variant, dubbed the J-31B, has even been depicted with unique side weapons bays, each capable of carrying 2 missiles, a novel feature that would set it apart from the single missile side bays of the F-22 and J-20, and could push its total internal air-to-air load to 8 or more missiles. Such a capacity would transform the aircraft into a dedicated arsenal plane, a missile truck capable of engaging numerous targets based on data provided by other networked assets. While optimized for air superiority, the J-35 retains significant multi-role capability. Its total payload capacity is a substantial 8,000 kiloliters, divided between 2,000 kg internally and 6,000 kg on 6 external hardpoints for non-stealthy missions. In this beast mode, it can carry a wide array of munitions, including up to a dozen small-diameter bombs for precision strikes or large air-to-surface, anti-radiation, or anti-ship missiles, making it a versatile platform for both air superiority and maritime strike missions. When placed in a comparative context, the J-35 reveals itself as a product of a distinct strategic and industrial environment. Against its most obvious analog, the American F-35 Lightning II, the J-35 presents a study in contrasts built upon a foundation of striking similarity. The J-35's twin-engine configuration offers potential advantages in top speed, which is estimated to be between Mach 1.8 and Mach 2.2 versus the F-35's Mach 1.6, as well as the inherent redundancy and safety margin that is highly valued in overwater naval operations. This, however, comes at the likely cost of a larger infrared signature, greater fuel consumption, and increased maintenance complexity compared to the F-35's single, powerful F-135 engine. The F-35's undisputed trump card remains its mature, combat-proven sensor fusion, its seamless network-centric warfare capabilities, and the vast global logistics and support network that underpins its operations. The J-35 appears to counter these systemic advantages with platform-specific strengths: a potentially larger internal air-to-air missile payload and the longer reach of its PL-15 missiles. The persistent and undeniable visual resemblance between the two aircraft continues to fuel the debate over whether this is a case of industrial espionage or simply the convergent evolution of designs shaped by the same unforgiving requirements of stealth and performance. The comparison with Russia's Sukhoi Su-57 Felon is even more revealing, as it highlights two fundamentally divergent philosophies on what constitutes a fifth-generation fighter. The J-35, like the F-35, is a design that prioritizes all-aspect, broadband stealth above all else. The Su-57, in contrast, makes a deliberate trade-off, sacrificing a degree of all-aspect stealth for superior raw kinematic performance, including extreme supermaneuverability enabled by 3D thrust vectoring and the ability to carry very large, long-range hypersonic weapons in its capacious internal bays. The Su-57's doctrine for countering stealthy opponents relies less on its own low observability and more on its powerful sensor suite, including unique L-band radar arrays built into its wing leading edges and a sophisticated infrared search and track IRST system to detect and engage low RCS targets. The J-35 is a direct challenger to the F-35's stealth-first, information-centric design paradigm. The Su-57 is an attempt to create an alternative to it. This reveals a deeper battle of doctrines. The F-35 is conceived as a single node within a vast, distributed, and networked combat system, where the collective situational awareness of the system itself is the primary weapon. The J-35 is being developed to integrate into a more centralized, state-controlled battlespace network, optimized for regional dominance. The Su-57, with its emphasis on individual platform performance, represents a more traditional approach, where victory is sought through the superior speed, altitude, and agility of the fighter itself. The outcome of a future conflict between these machines may well be determined by which of these deeply ingrained philosophies proves most resilient and effective in the chaos of modern warfare. The strategic calculus behind the J-35 program is twofold, reflecting its dual identity as both a carrier's sword and an exporter's gambit. For the plan, the J-35 is the critical enabler of its long-held blue water Navy ambitions. When paired with the Type 003 Fujin and its electromagnetic catapults, it creates a carrier strike group with the reach and penetrating power to challenge American naval supremacy in the Indo-Pacific and beyond. It transforms the Chinese aircraft carrier from a largely defensive asset, limited by the performance constraints of ski jump operations, into a true instrument of offensive power projection, capable of launching sustained, stealthy strike operations far from the protection of mainland air defenses. In its other guise as the FC-31, the aircraft is a disruptive force on the global arms market. It is being aggressively positioned as a more affordable stealth fighter alternative for nations that are either unable to purchase the F-35 due to political restrictions or unable to afford its high acquisition and operational costs. With a speculated price tag of around $70 million per unit, it significantly undercuts not only the F-35 but also some European 4.5 generation fighters like the Rafale and Typhoon. Pakistan has emerged as the most prominent potential customer, with negotiations reportedly concluded and Pakistani pilots allegedly sent to China for training on the new aircraft. For Pakistan, the acquisition of a stealth fighter would fundamentally alter the regional military balance with India. Other potential markets are being explored in the Middle East and Africa, where the FC-31 offers a path to fifth-generation capabilities without the political conditions often attached to American arms sales. This dual identity, however, creates a fundamental tension. To be a credible naval fighter capable of confronting the U.S. Navy, the domestic J-35 must be equipped with China's most advanced and sensitive technologies, from the WS-19 engine to its metamaterial coatings and sensor fusion software. To be a successful export product, the FC-31 must be affordable, reliable, and stripped of these very same crown jewel technologies to prevent compromise. Managing this divergence between a high-end domestic version and a downgraded export model will be a significant and ongoing challenge for Shenyang and the Chinese state. By exporting the FC-31, Beijing is engaging in a form of stealth diplomacy. It is not merely selling hardware, it is selling strategic influence, creating new security partnerships and technological dependencies that are centered on Beijing, thereby directly challenging the existing U.S.-led global security architecture. The journey of the Shenyang J-31 from the smoky, underpowered FC-31 prototype to the sleek, carrier-borne J-35 is a powerful testament to the speed and scope of China's military-industrial evolution. It is an undeniable achievement, demonstrating a rapidly maturing capability in complex aerospace design, advanced material science, and large-scale systems integration. The aircraft can no longer be dismissed as a mere copy or a paper tiger. It is a formidable contender that has earned its place among the world's elite fifth-generation fighters. It is a machine that looks impressive on paper and, unlike some of its more temperamental predecessors, does not appear to require a ritual dance to start up. Yet its final chapter has yet to be written. Its ultimate standing in the pantheon of modern combat aircraft will not be determined by airshow demonstrations or the carefully crafted narratives of state media. Instead, its true measure will be defined by the answers to three crucial and as yet unproven questions. First is the industrial challenge. Can the advanced WS-19 engine be mass-produced with the consistency, reliability, and service life required for high-tempo naval operations? Second is the software challenge. Can China's engineers develop sensor fusion algorithms that are not just comparable in function, but truly mature and resilient in a ferociously contested electronic warfare environment? And third is the human challenge. Can the People's Liberation Army Navy master the fiendishly complex, perishable, and unforgiving art of sustained blue water carrier aviation on a timescale that matches its technological ambition? The Shenyang J-35 is a potent symbol of a shifting global power balance, a credible threat in the contested skies of the Indo-Pacific, and a machine that warrants serious, sustained, and clear-eyed analysis for the foreseeable future.